Hello, this is Emad Mirabi. I want to share a short sample of my teaching lessons with you. Let's start. About electric forces, last session we learned that based on Coulomb's law, electric forces are given by the formula F is equal to K Q1 Q2 over R squared. So 2 point charges close to each other, they will apply force to each other, and if the signs are the same, the force is a repulsion force, and if the signs are the opposite, force is an attraction force. Now we want to talk about superposition of electrostatic forces. If a charge experiences force from multiple other charges, the net force is a vector sum of all individual forces. For example, here we have some charges. Assume that this is Q1, and then this is Q2, and then this is Q3. And this is a test charge here. First, we concentrate on Q1 and neglect these two charges. So what is the force applied to test charge Q if there is only charge Q1 around it? So if they are the same size, for example here, they're the same sign, so the force F1 is a repulsion force. Now we concentrate on charge 2 here, and we neglect these two charges. So if there is no other charges but charge Q2, for example, assume that the charge Q2 is repelling the charge Q, the test charge Q, so the force will be like this, F2. And then let's concentrate on the charge Q3 here and neglect about Q1 and Q3. For example, if here again the force is a repulsion force, now we can add these three vectors to find the net force that this charge Q, this test charge Q experiences in this case. Here, for example, they are perpendicular to each other and they are in a square formation. Therefore, the resultant of F1 and F2 is like something like this, and they will be added by F3. So the resultant force is something like this, but the magnitude must be greater, of course. The magnitude must be greater. So whatever it is, superposition of electrostatic forces says this. It says you can think of the forces one by one, and then you can calculate the vector sum of all those forces to find the net force. Okay, let's do examples. Two charges Q1 and Q2 are placed at 0 and 4 meters respectively. So let me draw a x-axis, for example, here. This is the this is the point 0, and this is the point 4. Here we have the point charge Q1, and here is the point charge Q2. Both of them are positive 2 microcoulomb. They are placed at 0 and 4 meters respectively. The question says find the net force on a test charge 1 microcoulomb placed at the midpoint. So here we have So the question says here we have a test charge Q, which is positive 1 microcoulomb. Let me draw it here. So this is a test charge which is 1 microcoulomb here. Because this charge was positive 2 microcoulomb and this charge was positive 2 microcoulomb, so the force applied from Q1 is F1, like this. It's a repulsion because both Q1 and Q are positive charges. And now we focus our attention to the force that Q2 applies to test charge Q. So the force is F2. It is again repulsion. Can we say that the magnitude of F1 and F2 are equal to each other? Yes, because the charges are the same and the distances are the same. So the magnitude of F1 is equal to F2, but direction of F1 and F2 are opposites, and therefore the resultant force that the test charge Q experiences is 0. We can show the magnitude of a force with like this, or I can put it in a norm like this. If I put a vector sign, I can put it in a norm or absolute value to show that this is the magnitude of this vector. Okay, so in here I didn't calculate the forces F1 and F2 because I knew that based on this formula, we had this formula of Coulomb's law, F is equal to K Q1 Q2 over R squared. For example, if I want to calculate F1 will be K is 9 times 10 to the 9. F1 is let me substitute Q1 and Q2. So let me here for the force F1 and F2, it is Q times Q2 or Q times Q1. So 1 microcoulomb times 2 microcoulomb over the distance is 2 meters. So 2 is squared. So it will be 9 over 2 times 10 to the negative 3 Newton. Or we can say 4.5 millinewton is the magnitude of force F1 and F2. Both of them are the same size because Q is the same, Q1 and Q2 are the same, and the distance are the same. So the magnitude of F1 and F2 will be the same. We found that direction of F1 and F2 are opposite, so the resultant vector is 0. Find the net force on the test charge. The net force will be found to be 0. Here's another example. 3 charges Q1, Q2, Q3 are placed at the corners of a right triangle. Find the net force on charge Q2. So the question is asking to calculate the net force on the charge Q2. L, the length of this isosceles right triangle, is given to be 1 meter. Q1 is 3 microcoulomb, Q2 is negative 1 microcoulomb, and Q3 is 4 microcoulomb. So again, based on superposition of electrostatic charges, what is the force Q2 experiences from the charge Q1? It's an attraction force. It's an attraction force like this. It's like this. So F1. What is the force? Let me calculate F1. let me calculate the magnitude of F1. F1 is K Q1 Q2 over L squared. So K is a constant, 9 times 10 to the 9, and then Q1 is given to be, the magnitude of Q1 is 1 microcoulomb, Q2 is 3 times 10 to 3 microcoulomb times 1 microcoulomb here. So 3 times 10 to the negative 12 will be the numerator, and in the denominator we have 1, and therefore it can be written as 27 times 10 to the negative 3 Newton. So 10 to the negative 12 times 10 to the negative 10 to the 9 will be 10 to the negative 3, and then 9 times 3 will be 27. So the magnitude of F1 is 27 millinewton. It's an attractive force like this. What about the charge Q3 and the force Q3? The force Q3 will be again an attraction force like this. So F3 will be like this. I drew the F3 greater than F1 because I know that the magnitude of the force is greater, because the charge is greater. The distances are the same, but the magnitude of Q3 is greater. So now again, let me apply the Coulomb's law formula. K Q1 Q3 over R squared, 9 times 10 to the 9, and then again 1 times 1 microcoulomb, 4 microcoulomb will make 4 times 10 to the negative 12. Denominator is 1, so it is 36 times 10 to the negative 3. Let me rewrite these numbers to be 9 times 3 millinewton and 9 times 4 millinewton, because I want to show that they are Pythagorean. They will make a Pythagorean triple, and the resultant force will be like something like this. The resultant force will be something like this. Let me call this F net or F total. So the magnitude of F nets, so I can write the magnitude of F net to be 9 times 5 millinewton or 45 millinewton. 45 times 10 to the negative 3 Newton. How did I got this number? Because of Pythagorean triples 3, 4, 5. When I rewrote these, I found that if this is proportional to 3 and this is if these lengths are proportional to 3 and 4, the hypotenuse will be 5. So 3, 4, 5. Okay. Now, what can be said about direction of the net force? The direction of the net force, because we have a 3, 4, 5 triangle, the angles are 37 here and 53 here. So we can either say the direction of the net force is about direction of the net force. We can say it is 37 degree west of the south, or we can say 53 degree south of west. So this is direction of the net force, and we found the magnitude of the net force. So again, in this problem we applied superposition of electrostatic forces. We took the forces one by one and added the resultant vectors.